This masonry design tutorial is brought to you by the Upstate New York chapter of the Masonry Contractors Association of America. I am David Beggs of Beggs Consulting Engineering, and I'll be discussing masonry bond beams as diaphragm chords. This topic was chosen because diaphragm chords are sometimes overlooked by engineers. The chapter sponsors educational programs for designers and masons to promote quality design and construction. Its motto is, if it's good for masonry, it's good for us all. According to the Masonry Design Standard, TMS 402, Building Code Requirements for Masonry Structures, a diaphragm is a roof or floor system designed to transmit lateral forces to shear walls or other lateral load resisting elements. So, whether the diaphragm is part of a load-bearing structure or a frame structure, it is part of the lateral load system and must provide a complete load path to the lateral bracing. One way to visualize the importance of the diaphragm to the masonry can be seen in the load distribution from the walls to the roof and then the roof to the shear walls. Here we see a building with no roof diaphragm. The lateral loads, either wind or seismic, cause the walls to cantilever off the foundation because there's no top support. The wall deflects inward, becomes unstable, and will likely collapse. This could happen if the actual roof diaphragm does not function properly. So, for a safe, strong building, we need a proper roof diaphragm. While the following examples are based upon a one-story building, the discussion of diaphragm chords applies equally to the floors and roof of multi-story buildings. Here we see the previous building, but now with a roof diaphragm. As the wind or seismic forces impact the building, the walls span vertically, producing a load at the top of each wall as well as the foundations. The top of wall load transfers to the edges of the roof. These edge of roof loads are due to either the summation of the wind loads on the windward and leadward walls or the seismic loads from the walls and roof. Then the diaphragm distributes the loads to the side edges of the diaphragm by shear. And finally, the edge shear is taken down into the shear walls and foundation, thereby completing the load path. When the diaphragm transfers the load to the shear walls, it is acting as a horizontal beam. The bending creates tension and compression in the chords. The flexibility of the diaphragm will also determine how much the top of the walls are displaced. The moment it is developed can be resolved to determine the actual chord forces. If strength level loads are used, the area of reinforcement in the diaphragm chords can be determined. Let's look at diaphragms in general. Diaphragms are typically classified as either flexible or rigid. They can be classified as something in between flexible and rigid, but that's rarely done. The classification is important because diaphragm stiffness significantly determines how the roof lateral loads are distributed. For example, here we see that flexible diaphragms distribute lateral loads based upon tributary area. Flexible diaphragms are usually constructed of wood framing or steel framing and metal deck. The diaphragm chords must also be continuous between supports. Rigid diaphragms differ in that they are much more stiff, which affects how lateral forces distribute to the braces or the shear walls. The distribution is determined based upon the relative stiffness of the shear walls or bracing themselves and usually result in building torsion. Rigid diaphragms are generally constructed from cast-in-place concrete, precast concrete, or concrete on metal deck. The purpose of this tutorial is not to teach how to design diaphragms. There are many material-specific resources for that, such as the Design Guide for Reinforced Diaphragms from the Concrete Reinforcing Steel Institute based upon ACI 318. There is also the Diaphragm Design Manual by the Steel Deck Institute. And finally, Diaphragms and Shear Walls by the American Plywood Association. This tutorial addresses masonry walls as the chords of the diaphragms. So let's review everything that's happening at the top of the walls. Here we see a typical bar joist and metal deck roof. We'll use it as an example to describe the structural actions with the bond beam at the top. First, the bond beam acts as a bearing point for spreading and distributing the gravity loads from the roof framing into the wall below. It also acts as a tie-down anchorage for roof uplift. The anchorage for the uplift load path must be continuous with the vertical reinforcement. A third function is to laterally brace the top of the wall. Finally, it can be the diaphragm cord if properly detailed to transmit both tension and compression. This multi-use of the bond beam is structural efficiency. While the bond beam appears simple, all of the bond beam features must be fully detailed for the mason to construct the walls. Looking closely at the top of wall detail, we see it has a bond beam. On this detail, the bond beam has a solid bottom. So one detailing improvement that is essential is to provide an open bottom to the bond beam rather than the closed version shown to allow the vertical reinforcement to extend through without having to core the units. Most manufacturers make these open bottom units. It's important to anchor the vertical bars against roof uplift by hooking them or developing them above the bearing. As previously described, the bond beam serves many functions, including that of the diaphragm cord. The reinforcement is designed for the cord forces. The engineer for this detail chose to include an edge angle to provide additional support for the metal deck at the wall. Not all engineers provide this angle. While it says the angle is continuous, it is generally not interpreted as one piece or with welded joints. Full continuity of the angle could provide added cord capacity. You can't ignore the non-load bearing wall. On this detail, the bond beam has an open bottom as recommended on the last slide. While the wall is non-load bearing, it's also a shear wall. So it's important to transfer these shear forces from the diaphragm into the continuous angle, through the bolts and into the wall. These bolts must take shear in plane of the wall, out of plane, and for gravity loads and uplift loads for the roof. Each engineer develops their own method of bracing the top of the wall against out of plane loads. It's unlikely the metal deck can serve this function alone. Thus, a series of horizontal bridging, diagonal bridging, and supplemental bracing must be designed to accommodate the imposed forces. Part of proper detailing of the diaphragm chords includes the continuity we've already discussed. Here's an elevation of a building with the wall movement joints. The elevation was created using the Direct Design software, a masonry program based upon TMS 402 and sponsored by the National Concrete Masonry Association. The joint locations are selected by the user, but the diaphragm cord reinforcement is designed by the software. The user can select whether the diaphragm is either flexible or rigid. While the movement joints separate the wall into panels for crack control, the diaphragm cord must be continuous between lateral supports. Without the continuity, the cord tension or compression would not be developed and the load path would be incomplete. Remember to consider continuing the cord reinforcement around corners as well to create the anchorage. We continually stress that diaphragm cord continuity is essential. Here's a possible plan detail at the movement joint at the bond beam. The reinforcement must be continuous through the joint with a full lap splice. However, you still want the appearance of the movement joint. One option is to have the mason rake the mortar at the fascias and add sealant. For more information, see the National Concrete Masonry Association's Tech Notes. Tech 10-2C specifically provides construction details for movement joints. Engineers should analyze the bond beam using the reduced width of the joint as well. Here we see the previous example building, but now we're reminded that we must look at the diaphragm from the perpendicular direction also. This will give stability for all the walls. In summary, design the diaphragms for both shear and moment capacity. This is required for stability of the masonry walls. Masonry bond beams can function as diaphragm cords. Anchoring the diaphragm is essential. This includes all out-of-plane as well as in-plane effects. Check that there is a complete load path. Provide continuity of the diaphragm cord between bracing elements. Finally, we want all of this to be constructed properly, so convey the details fully to the mason contractor for proper installation. In this program, we mentioned the Direct Design software. Visit the website of the National Concrete Masonry Association to find out how you can obtain a copy. Another excellent modeling software designers is Masonry IQ by 3D-IQ. For many more resources related to BIM for Masonry, visit the BIM-M website. This tutorial is just one of the educational presentations developed by the Upstate New York Masonry Contractors Association of America to help make masonry more effective to design and easier to build. This has been David Beggs. Thank you for watching. If you have any comments or would like to see more topics, please contact the chapter at our website.